Okay, so in this video, we're going to discuss probability, and we're going to be using these notes to run through everything that is needed in preparation for your exam. So the few things that you have to take note of is that probability is just the likelihood of events happening. That's what we're interested in. And there are a few key points that we're going to be needing later on. So this should have been put at the end, but either ways, we're just saying if two events are happening at the same time, or we're just saying we have a choice between two events, let's call it A and B, the probability of them happening, or one of them happening, is simply going to be written as the probability of A union B. And if we are saying the probability of both events happening, meaning these events have something in common, that's P, the probability of A intersection B. Then the probability of an event not happening is simply the probability of that event complement. That's how we indicate it. Okay, so this was supposed to be put at the end. So just ignore this for now. We're going to discuss this later on. There are, of course, terms we'll be using like mutually exclusive. We just mean those events that we're discussing have nothing in common. Yeah. And when we say events are independent, we just mean that the occurrence of one event B will not affect the occurrence of A. That's basically what we mean. Yeah, so okay, we'll discuss this later on. So the first thing that we're going to start with are terminologies that are used in probability. And when they talk about an experiment, we're just saying this is a repeatable process that gives rise to the number of outcomes. An event is simply a collection, or rather one or more outcomes. That's what we call an event. A sample space is a set of all possible outcomes. So all the alternatives that can be given to an event happening in an experiment is what we call a sample space. So whenever these outcomes are equally likely to happen, the probability of event is the number of outcomes in the event divided by the total number of possible outcomes. So probability is simply the likelihood of something happening over the other outcomes, other chances that you have in the same, in the experiment, or where that A is found. Yeah, so let me give us a certain, this is a best example that we can look at. So a fair die has each face numbered 1 to 6. The die is thrown once and the number landing face up is recorded. Find the probability of the die landing with the number 5 face up. The probability of you having 5 on the die when it lands is simply 1 over 5 because there's only one face that has a 5. So how many faces are there? It has 6 faces. So you have 6 outcomes that are likely to happen, but 5 is only in one of those faces. So the probability of 5 appearing is just 1 over 6. This is where the 1 over 6 is coming from. Then look at this guy here. They're saying find the probability of throwing an odd number. So if you look at all the numbers between 1 and 6, they're saying, here we're saying the event throwing an odd number has 3 outcomes because you are listing 1, 2, 3, 4, 5, 6. Your odd numbers are just 1, 3, and 5. So you can either get 1, 3, or 5. These are the only odd numbers that you have on the face of the die. So meaning you have 3 alternatives, 3 possible outcomes over the total number of outcomes, which is just what? 6, because there's a chance that you may not get something that is odd. Yeah. So how many things can show up? We have 6 faces, right? On those 6 faces, for you to win, imagine getting an odd number is you winning the whole experiment. We're just saying you have 3 chances of you winning. That's 3 over what? This is just same as 1 over 2. That's the 3 over the 6. I hope this makes sense. This is just trying to stress the whole idea of what we mean by probability. According to the definition, we said probability is the number of outcomes that you're expecting over the total number of likely outcomes. So yeah, hope that makes sense. 2 fair spinners each have 4 faces numbered 1 to 4. So there are 2 of them. 1, 2, 3, 4. So there are 2 of them. The 2 spinners are thrown together and the sum of the numbers indicated on each spinner is recorded. So we have 1. Okay, I'll put the other guy here. 2, 3, 4. So if 1 and 1 shows, the summation will be, so let me just, the likely chances. So meaning the ones in blue are the summations. So this can be 3. If 1 and 3 shows up, the sum will be 4. If 1 and 4 shows up, the sum will be 5. So this will just be a 3, this will be a 4, this will be 5, this will be 6. We're adding, that's a 4, it's a 5, 6, 7, that's a 5, 6, 7, 8. So look at the questions here. They're saying find the probability of the spinners indicating a sum of exactly 5. How many 5s do you get as the sums here? So we're getting this 5. There's also this 5 there. There's also this 5 and there's that 5. The outcomes are 1, 2, 3, 4. That's 16. So you have 16 outcomes with a chance of getting 5 being 4. So we're going to say it's simply 4 over 16. So this is just going to be 1 over 4. This is the chance of you getting the sum being exactly 5. More than 5, so more than 5, right, means 6 or 7 or 8, right? So we have 1, 2, 3, 4, 5, 6. So it's going to be 6 over 16, which is just 3 over 8. This is the chance of you getting something more than a 5. So this is what you're supposed to get here. So this is how they get the 1 over 4. That's how they get the 3 over 8. Hope that makes a bit of some sense. All in all, we're just trying to stress the whole point of you understanding what we mean by probability. Now we have a nicer way of showing this. This is using Venn diagrams. So a Venn diagram, we know what it is from sets. If you did sets, so a Venn diagram looks like this. You have sets. So now this Venn diagram, we can call it a sample space. It has samples inside these sets. A rectangle represents the sample space and it contains closed curves that represent events. For events A and B in a sample space, so we have the 2 events, and these events have something in common, which is this middle part, that's their intersection. And if we wanted to talk about their union, we would just get everything. If we want to talk about things outside A, the complement of A, we mean everything else happening outside A. That's what we mean by A complement, and it's indicated by this. So the probability of A not happening is equal to 1 minus the probability of A happening. Why? Because there's a rule that says all probability values are going to be either, they are found here. So probability of an event happening is always going to be between 0 and 1. That's a property of probability. So 0 being the certainty that something is not actually happening, that's 0. Then 1 being the certainty that something is surely going to happen. For example, today, this is in May, the chances of it, the 20th of May, right? So the chances of it raining today is 0. So we are certain, unless otherwise, but we are very much certain that it's not likely to rain. So that is when something is not likely to happen, the probability is 0. We are certain. Then if the probability of something happening is well known and it's 99% accurate, we are certain, that's 1. The probability is 1. But if otherwise, if there is just a chance that things may go in other directions, the probability is always between 0 and 1. So hope this makes sense. So here they've given us an example to use a Venn diagram to illustrate, to find either the intersection, the union, the complement, and everything else that is needed. So here they're telling us to say a card is selected at random from a pack of 52 playing cards. Let A be the event that the card is an S, and D the event that the card is a diamond. Find the probability that it's both an S and a diamond. Probability that it's both. It can be either an S or a diamond or either of the two. The third one, the probability that it's not an S, then the probability that it's not an S and it's not a diamond, complement, right? So this is what we are interested in. So in the Venn diagram here we are given, we know according to, we have 52 cards. So in the 52 cards that we have, there are 13 diamonds and 4 S's. But there is only one card that is both. So this is the one that you're seeing here in the middle. So meaning the other 3 S's are not, there should be a spade, there should be a heart, there should be the other guy. So that's making them 3. Together are 4, right? In ASs are 4 in total. Then diamonds, there should be 13. So this is the 13 you are seeing, meaning the other guys are outside, right? That's the 36 that you're seeing this side. So that's what you see. Then that's the 36 that you're saying. So the first one, they're saying the probability that something is both an S and a diamond is simply going to be 1 over 52, right? It's 1. There's only one card that is both. Then the probability of something being A union D, meaning being an S or a diamond or both, yeah, or just a diamond but not an S. So we just sum up everything. A union, meaning union, you add everything. That's 13 plus that's going to give us a 16, if I'm not mistaken. That's a 16 over a 52. You reduce this. This is going to be what? Is it a 26? Is it? You reduce this. That's going to be a 4. Then you put 13. So you get something like that. So A union. So this should give us 4 over 13. That's what we have. That's the union. Then here, they want us to get the complement of A. What is the probability of something not being an S? So the probability of something not being an S means everything outside A. So this is everything outside A, this part here. So meaning it's just 12 plus 36. So if I may erase it so that you see it. So what is the number of cards that are outside A? That's what we're interested in. So we're having a 36 by 12. That's going to give us a 48. So the answer is 48. Here the probability is just 48 over 52. That's the answer. You can reduce this. 4 there is 12. 4 there is just 13. Or if you wanted, you would have gotten the probability of something being an S, which is just 4. We say 4 over what? The probability of A is what? 4 over 52, which is just 1 over 13. Then subtract this from 1. So the probability of something not being an S is just 1 over 13. This will give you exactly 12 over 13. Then what is the probability of something not being an S and not being a diamond at the same time? So this should just give us what is A intersection B. So this is the same as 1 minus the probability of something being an S and a diamond, which we already got at the beginning. That's 1 minus. So this was 1 over 52. So that's 1 over 52. This will lead us into 51 over 52. So this should make sense. Yeah, so this should be able to make sense. Yeah, so the probability of, oh, so this is a complement. Sorry here. Or here, the complement is not outside. The probability of this here, I think they made a mistake here. Here you look at this. They've gotten the complement of A, then intersected with D. Yeah, so if that's the case, would have to get what's the complement of A. So the complement of A, so this is just going to be, they didn't follow the set which is here. If we do our set here, the answer should be 51 over 52 because it's a complement of A intersection D. But here they are solving for the probability of A complement intersection B. That's what they've done in the working. So the complement of A is everything outside A, right? Everything outside A, which is 12 and 36. Then we want to intersect it with D. Sorry, this is D here. So everything outside A, I'll use red. That's what you're seeing there. So I'll use red. Then B, I'm going to use blue to shade everything in. They're saying intersect with D. So D is right here. That's the only part where they're intersecting. So the answer is just going to be a 12 over your 52. That's going to be a 6. That's going to be 26. That will be a 3. Simply over 13. This will be our answer, 3 over 13. Yeah, so they had a mismatch in their question. Here they showed this. They should have been solving for the complement of A intersection D. Yeah, so hope you noticed that. So that's simply the first example that you can relate to in terms of using a Venn diagram. So you can try to pause the video, attempt this question here first before you play to see if you're following. So they're saying here we have to recreate the Venn diagram ourselves because they've just given us the information here. They're saying in a class of 30 students, 7 are in the choir, 5 are in the school band, 2 students are in the choir and the band. A student is chosen at random from the class. Draw a Venn diagram to represent this information. Find the probability that. So first of all, we are simply going to start with doing this. So we have the choir, I'll put C there. Then in the band, in the school band, we'll put a B. Then there are 2 students who are both in the choir and in the band. So 2, then there should be 7 students in the choir. So 7 minus 2, that gives us a 5. Then there are 5 in the band. So 5 minus 2 gives us a 3, because the total in the band should be 5. The total in the choir should be 7. So hope that's okay. But then there were 30 students in total. So where are the rest? The rest do not take part in either the choir or the band. So we can subtract. This is simply 5. I mean, this is 7, this is 10. So meaning we have a what? Is it a 40 outside? Or it was 30 in total. So this is going to be what? 30 minus 10. This is 10. 5, 2, 3, that's a 10. So subtract from 30, meaning we have 20 students who don't participate, right, in anything, in either the band or the choir. So now they are saying, find the probability that the student is not in the band. So the probability for the student to be outside, so complement of the choir and the band, is simply 20 over what? Over 30. This is just going to be 2 over 3. That's the answer there. The student is not in the choir, nor in the band. So what will be the probability there? Try to think about it before I share with you what we're supposed to do. Okay, so here for the first one, for B, let me just correct my statement. Here they are saying the student is not in the band. So in the band, right? Not in the band and not in the choir, but they're just saying specifically not in the band. The band is B, which is 3 and 2. So if someone is not in the band, meaning it's what? 25 over what? 25 over 30. Yeah, so let me just correct that. That's 25 over a 30. That's going to give us a 5, and that's a 6. Hope this is okay. Hope that's okay. So I've made a correction here, guys. Here, hope you're able to see this, Madali. So they are simply saying the student is not in the band. This is the band, right? We have the band and the choir. So that's a 25 over 30. Then for C, the student is not in the choir nor in the band. That's why we do the 20 over 30. So yeah, the first one I did is supposed to be for the last one. So hope you see that. Hope this makes sense. Okay, so you can do this just for your own verification. Yeah. So just a notice here, just an addition to what we've been doing. So we're saying there is a formula that we can be using to simplify things. So there's this formula here to say the additional rule of probabilities. So many probability problems are best solved by using the addition rule formula to find the probability of both A and B happening at the same time, then drawing a Venn diagram to find the other probabilities. So we're just saying the probability of A union B happening is the same as the probability of A, then plus the probability of B, then minus the probability of A intersection B. So we can make this to be the subject of the formula by taking these two on the other side. Yeah, so we can just take this guy on the other side and take this back. So it's going to be P intersection A. The probability of A intersection B is equal to the probability of A plus the probability of B, then minus the probability of A union B. So we can have that as well. So this is a typical example given down here. So if you look at this example here, so in this example, they're saying A and B are two events where the probability of A is 0.6, the probability of B is 0.7. Their union is that they're asking for the probability of A intersection B. Yeah, so this can be gotten from our formula. So we can just apply our formula. We're saying the probability of A intersection B is equal to the probability of A plus the probability of B minus their union, which is 0.9. This is going to be 1.3 minus 0.9. This is going to be a 0.4, if I'm not mistaken. Yeah, that's what you get. Let's see. Okay, so that's what they got as well. Then once you get the probability of the intersection, we can easily get anything else that we are looking for. We can create a Venn diagram. So a Venn diagram can make life a bit easier. So in the Venn diagram, we can show these probabilities as if they are just elements. So we create a Venn diagram that shows that, first of all, these guys are not mutually exclusive, so they do have an intersection. No wonder we're going to join them like this, and the intersection we're from getting is 0.4, and the A alone, so we can have the probability of A, we say the union, everything is 0.9, so let's say that's going to be 0.9 minus this, that's going to be a 0. This is going to be, should be a 0.2 if I'm not mistaken. Then for B to be 0.3. Yeah, so the total here you are seeing is 0.9, right? Then the probability of A is 0. What? 0.6. I'm just subtracting 0.6 minus 0.4. That's how we get this then. The outside, because the total should have been 1, right? So now the outside here is going to be 0.1. So hope you are seeing this is 0.9. That's their union, meaning what's outside is 0.1, because the total of probability should always amount to a 1. Hope you get that part. Now, if they ask us for the probability of A complement union B, A complement is 0.4, union B brings back everything, that's going to be 0.4 plus this, that's going to be 0.8 if I'm not mistaken. So we're going to get, this is the probability of A, they've given us is that, A complement. Oh, this is B here, sorry, this is B here. What is the probability of A? So the probability of A complement is just 1 minus the probability of A. So we already have the probability of A, which is 0.6. You can just look at it here. What is outside A? A is here, so the guy that I'm going to show in blue, that's A complement. This whole part outside, which is 0.3 plus 0.1, which is the what? The 0.4. So no wonder the Venn diagram is very much advisable, because it makes things way easier. Then C is the one that I was explaining. A complement, what is outside A? Union, what's in B? So that's going to be 0.4, because union brings back what was excluded. So 0.4, 0.3, 0.1. The total will be 0.8. That's your C. Then for this one here, we're saying A complement intersection B. That's just going to be 0.3. Yes, we have 0.8 and 0.3. So hope you are seeing that. Yeah, so these are the answers there. So treat these probabilities as if they are just elements in a set. Then everything else will make sense. Yeah, so that's how you can easily come up with the solutions to these. Okay, so here now we want to talk about conditional probability. So this is the type of probability where two events are a bit related, or one has occurred before the next happens. Yeah, so we may say in those terms. So the probability of an event happening when something else has already been given is always going to be called conditional, because sometimes the first event that happened can affect the second event, or in a way that the second event can be affected, or how it happens is affected. Yeah, so to say, for example, a typical normal illustration I may give is, if let's say you have 5 apples and you get one without replacing it, and then we ask you the probability of getting the second apple from the same bag. So now your probability of the second pick has been affected by the first pick, because you didn't replace the first one that you got. So we're saying the probability of B happening given A is the same as the probability of B intersection A divided by the probability of A. Right? This is what we mean by conditional probability. We're going to be illustrating it like this. And don't forget, we said when it comes to the addition of probabilities, remember what we learned. We said this is the same as the probability of A plus the probability of B. Then we said minus the probability of A union B. So don't forget that formula. This guy is going to come in handy. Yeah, because here we've just added, we have added the second formula, which is the conditional probability formula here. Yeah, so we have added this. So this generates what we call, this was the addition rule. Now we come up with a multiplicative rule that says the probability of B intersection A is equal to the probability of B given A times the probability of A. So this is a result of this second formula. So we have now the third formula. So hope you are keeping them in mind. Then they're saying we can also use the fact that the probability of A intersection B is, so we're just flipping it. You notice that if we say the probability of B intersection A, meaning B comes first given A. So if you flip it, even here the information changes. We're saying the probability of A intersection B is equal to the probability of B given A multiplying the B. So when A and B are swapped, it's the same thing. Yeah, so we can just switch this. This is the same as, we can flip it. That's what we are saying. If we say A intersection B, it will be the probability of A given B, then times the probability of B. So we can have that. So that's a multiplication formula. Please keep that in mind. So here we have an example. So the example here, they are saying two fair spinners each have 4 faces, numbered 1 to 4. The 2 spinners are thrown together and the sum of the numbers indicated on each spinner is recorded. Given that at least one spinner lands on 3, that's the first condition. You see that? That's the first condition. Find the probability of the spinners indicating a sum of exactly what? Exactly 5. Right? So the probability of something landing on 3, so we want to land on 3, right? The probability of us landing on 3 from the, so there are 4 faces, right? Meaning there's just 1 3, so the probability is 1 over 4. From the 4 faces, only 1 face has a 3, so this is the first probability. Given that the first probability is this, right? Can we now find the probability that the sum, the sum is going to give us what? 5. So how many ways can we get a 5? If we have, remember what we had written earlier on, we had something like this. There's a 3, there's a 4. So for us to get a 5, we said, remember we just said this is 2, 3, 4, this is 5, this is 3, 4, 5, 6, this is 4, 5, 6, 7, this is 5, 6, 7, 8. So for us to get the sum of 5, we're simply saying this is 1, 2, 3, 4, right? But then from these guys here that we are having, the probability of us getting a 5 is supposed to be 4 over the total options, with the total chances, the total sums, the recordings, which is 1 over 4. Now, in these ways that we've gotten a 5, where did we get a 3? So which of the following combinations allowed us to also work with a 3? So let me show this in purple. So how did we get this 5? We got this 5 by adding up 1 and 2. So this is not going to be part. Then here we got this 5 by adding a 3. So at least this is going to work. Yes, this choice works. Then this one here again works. This 5 also here works. So this 5 and this 5 are okay. This 5 here does not apply. So we just have 2 ways. Right? There are only 2 ways that we got a 5 where one of the spinner landed on a 3. Right? This is what you are getting here. So there are 2 out of the 4 ways. So here is what you have here. They're saying there's a clue in the question that we are looking for a conditional probability. As the question uses the word given, let A stand for the event at least one spinner lands on 3 and B be the event that indicates the sum to be 5. Draw 2 axes to indicate the values of each spinner. So we have this diagram. This is what we are having here. And like I said, there are only 2 cases where a spinner lands on 3 and the sum happens to be a 5. So we know that one of the spinners lands on a 3. This reduces the number of the outcomes where the sum is 5 to the 2 5s shaded. So this guy is here. That's what we are having. Then here we're saying there are 7 outcomes altogether where one of the spinners lands on a 3. So there are 7 in total where one of the spinners lands on a 3, right? But only 2 of them amount to the sum of 5, right? So the probability of at least one being a 3 is equal to, so initially we're saying the probability of a spinner landing on 3 initially is, so we're saying we can have a 3 there, so there are 7 in total, right? So we're saying 7 out of the 16 lands on 3. That's the first thing. That's the probability of A. Then the probability of B, we're saying the probability, there are at least 5 shaded this. So from these sums that we've gotten here, there are only 2 options where, there are only 2 results where we are getting a 5 and one of them was a 3. One of the spinners landed on a 3. These are the 2 guys that we're having. So 2 out of the guys that we've been given, which is simply 16. So this is what we're going to get. We're saying the probability of the sum being 5 and at least one of them being 3. That's the first thing, right? The probability of B given A is equal to this. So the sum being 5, at least one of them to be 3, right? That's what we're having. That's the condition. So there are only 2 of them, two landings out of the 16. And then from us getting a 3, at least one of them being 3, there are 7 landings. So this is what we're going to get. That's how they get the 2 over 7. So hope this makes some sense. So here now they're telling us to say we can just use this shrunken sample space method. We're saying at least one spinner lands on 3. This shrinks the size of the sample. So we're just saying the whole thing, the sum being 5. So we go back here. The shrunken space is where we just look at they're saying the sum has to be 5, right? So, and the choices, the condition, we follow the condition. A is what we are following. So A says we need to have one of them being 3, one of them landing on a 3. So 3, we have these 4 guys here and these 4 guys there. So we're having this part here. So now you have to count it like this. The number of times that one of the spinners lands on a 3 is simply 1. This is 2, this is 3, this is 4, this is 5, this is 6, this is 7, because we're having a 3 this side. We can't count this twice because of the 3 and the 3, right? So we just count it once. That's why the 7 is coming from. So from the 7, how many times do we get a 5? This is just going to be 2 times. So the shrunken method experiment will just request us to get the condition A and also the number of times that we're getting B in A. So there are 7 times that we're getting the sum. I mean, there are at least 7 times that 3 is going to show up. And of those 7 times, only 2 of them give us a sum of 5. So this is where the 2 over 7 is coming from. Yeah, so we can do it like that as well. So here now we want to discuss the application or the representation of conditional probabilities using a tree diagram. So we're just going to use this example here. They are simply saying the turnout of spectators at a motor rally is dependent upon the weather. On a rainy day, the probability of a big turnout is 0.4, and if it does not rain, the probability of the big turnout increases to 0.9. The weather forecast gives a probability of 0.5 that it will rain on a day of the race. Draw a tree diagram to represent this information. Find the probability that there is a big turnout and it rains. There's a big turnout, just the plain big turnout. So this is what we're going to have. So the 2 cases we may have is that it may rain, that's the weather forecast, this is 0.75, or it may not rain, this is what we're having. And if it rains, the probability here they're saying the big turnout probability is 0.4 if it does not rain. So here we're just saying the big turnout is simply going to be 0.4, and if it does not rain, it's simply going to be 0.6, the opposite, so the minus 0.4 minus that. Then if it does not rain, the probability of us having a big turnout is 0.9, meaning the probability of us having it not raining and not having a big turnout is 0.1. So this is what we are having. Yeah, so they gave us 2 conditions first. They're saying when it rains and when it does not rain, right? So they gave us this, we use this, subtract from 1, that's how we get the 0.25. Then if it rains and you have a big turnout, this is 0.4, meaning the opposite is 0.6. But if it does not rain, the probability of the big turnout increases to 0.9. That's a 0.9 you are seeing here. And this is going to be 0.1. Now, the questions are here. They are saying, find the probability that there is a big turnout and it rains, right? So if it rains and you have a big turnout, you can have, so if it rains and you have a big turnout, so you can have this probability here for it raining and you having a big turnout. So here we're simply going to multiply these two. We just say the probability that it rains and there's a big turnout, which is just going to be 0.75, multiplying 0.4. Here you get your answer. That's what you have. Then the next part, they're saying there's a big turnout, right? So they've just left it to be plain. There's a big turnout. Now it can either rain or not rain. So if you have a big turnout, let me just put this in red. So you can have a big turnout if you have this guy, or you can have a big turnout when you have this case, when it rains or when it does not rain. So you multiply this plus when you multiply these two. So this will give you the first case here. The second case, we're just saying it can either rain and there's a big turnout, or it does not rain and there's a big turnout, right? So those are the cases that we have. Yeah, so this is what I was just saying. Now, because here we are having what? We are having this, so let's see if we'll get the same outcome. So I was saying you can have a big turnout and it rains, or you can have a big turnout. I mean, it doesn't rain and you have a big turnout. So here you simply multiply 0.75 times 0.4, then plus you can have 0.25 multiplying 0.9. So let's see what we get. So according to my calculations here, I'm getting a 0.325. That's the probability that you're going to get. So they used the conditional probability and it gave them this. So they said it can either rain and there is a big turnout, or it does not rain and there is a big turnout. So the probability, the answer plus the probability found by multiplying along the branches of R to B. Yeah, so this is supposed to give us the same thing. So we are having 0.75, sorry. Yeah, this is 0.75, then times 0.4, then plus we are having 0.25 times 0.9. Oh yeah, the answer has to be the same here. Sorry, when you multiply this, I made a mistake. This here, the answer has to be the same. The answer is 0.525. So this is correct. Yeah, so these are the cases that you can have this or that. So we're adding. That's what you get. Okay, so you can attempt this example and just try to see if you're able to follow through. Don't forget the rules that we've discussed so far. So on the rules, we've discussed that the first one is when you have or when you need the intersection. So there's the addition one. We say it's a probability of A plus the probability of B minus their union. And the second one, just say the probability of A given B is the same as the probability of A intersection B, then given the probability of B. From here we created the multiplication one, which is the probability of A intersection B to be the probability of A given B times the probability of B. Yeah, so we created this other one. So these are just the formulas you're going to be playing around to attempt this, making sure that you hide the answers to just see if you'll be getting the right thing by the time you are done. You can do it in two ways, using the tree diagram, or you can just use a Venn diagram. Either ways, the answers must be the same. Yeah, so here now we're looking at mutually exclusive and independent events. So when we say mutually exclusive, we just mean that their intersection is 0. So the rules that we are from looking at, we're just modifying them, because now if the intersection, remember we said P intersection B is equal to P A plus the probability of B, then minus the probability of A union B, right? So if their intersection is 0, it only leaves us with one choice, which is making the probability of B union A to be the subject. That's simply going to be the probability of A union B to give us the probability of A plus the probability of B, right? That's what we are having. So this is where it comes from, this, because this guy is a 0, so we'll just remain with this. The addition formula changes, and it will only be this thing here. This is when two events are mutually exclusive. They have nothing in common, right? The occurrence of the first event does not affect the occurrence of the second event. That's basically what we mean. Yeah, so that also changes now, because now we are saying if the intersection, if their intersection is, so this is, that was for mutually exclusive. Now we're saying here, when one event has no effect on another, they are independent. Therefore, if A and B are independent, the probability of A happening is the same whether B has happened or not. So the probability of A given B is equal to the probability of A. So we have added on to the formulas. This is the fourth, if I remember very well. So meaning, we can use the formula for conditional probability to give the fact that the probability of, since remember we say the probability of A given B is equal to what? The probability of A intersection B over the probability of B, right? Now we're saying if these guys are independent, meaning the probability of A given A is to the probability of A, implies that the probability of A intersection B is just going to be this times that, which is the probability of A times the probability of what? Of B. So this is where the multiplication rule for independent events comes in. Hope this is okay. So we're just playing around with the formulas, and we've created the fifth formula now. This is the fifth one. So of course, this will be given in your formula sheet. Yeah, for you guys from Unilas, so they always give you this. Yeah, so now if we're given an event, so the application is still going to be with the use of the formulas, but the representation, we can still use the Venn diagram to do that. Yeah, and to show this here, look at this here, they're saying events A and B are mutually exclusive, meaning they have nothing in common, right? So you can just create a Venn diagram that looks like this. So we put our A here, treat them as if they are just elements, sets having elements. So the element in A is 0.2, the element in B is 0.4. That's what we're having. When they say the probability of A union B, we just mean it's the probability of A plus the probability of B. So this is just going to be 0.6. Hope that's okay. That's what you have. So that's 0.6. When they say the probability of A intersection B complement, so this is just going to be the same as the B complement is A. Now intersect with A, just going to be the probability of A. So this is just going to be 0.2. Then this one here, what is outside A is B. So this is 0.4. Then what is outside B complement, because this here is the same as the probability of A intersection B, then complement, right? This is an empty set. So if you complement an empty set, you get what is outside here, what is outside here. This is going to be an empty set too. There's nothing. Yeah, so this is what you're supposed to get. So the first one gives us that. The second one is 0.3. Then the last one, they're saying what? This is, yeah, because we're having P intersection. This is supposed to be A. Okay, yeah, sorry, my bad. I changed this. I forgot how to show this guy. This changes. Remember, under sets, when you introduce a complement, the union changes to intersection and the intersection changes to union. So this has to be A union B, then the complement outside. Because if you bring back the complement, this guy will change. It will flip to become intersection, right? Yeah, so this has to be P A union B. We know what this is. That's 0.4. We got it there. 0.6, I mean. So this is where the whole 0.4 comes in. Yeah, so I made a mistake there. The same thing that you do on sets is just what we've done. If you have two sets like this, you can simply bring out the complement there. If you introduce the complement inside, this changes to union. So yeah, that was my mistake here. So it has to be union. Yeah, this is when you're going to get that. So if you understand sets, this should be pretty straightforward. So when they say they are independent, remember what we said under independent. If two sets are independent, meaning their intersection, so meaning we say what? The intersection is equal to the probability of A and the probability of B. Why? Because we say A given B is the same as the probability of A, because the occurrence of B does not affect the occurrence of A. That's what we have. So here we'll just multiply them, which is 1 over 3 times 1 over 5. This is 1 over 15. Then this part here, we are saying this is going to be, we can come here and write it like this. Oh, they made us a Venn diagram here. We can just use it. So the probability of A intersection B is 1 over 15, right? So we are having the probability of we need the probability of A alone. Okay, so the probability of something not being in the intersection here, just being in A, is just going to be the probability of A minus 1 over 15 gives you this. That's where the 4 over 15 is coming from. Then 1 over 5 minus 1 over 15. That's why you're getting the 2 over 15. Then this is what you get inside here. The whole thing, if you sum up these guys, then subtract them from 1, that's why you get the 8 over 15. What is outside, that's how we get that number there, because the total has to give us a 1, right? Then from here you can pick anything that you want. B complement is just 4 times this guy, then intersect it with A, it's just going to be 4, right? 4 over 15, that's the answer to this one. This should be 4 over 15. Then this is going to be the probability of A union B complement. So this is just 8 over 15. Yeah, so we're just using this. Yeah, so as before. And the last one as well, you see that's 8 over 15. So the whole idea of sets still comes back. Here you just have to be playing around with the formulas. Yeah, so alternatively for the last one, they are showing you how we can do it. We can just get their complements, then multiply them, because they're still independent. So if two sets are independent, even their complements are also going to be independent. Yeah. Okay, so you can actually now do the rest of the examples. That's where probability ends from. The rest are just examples. These are the key points I was mentioning to say. They should have given us these at the end. So these are what you need to know and how to manipulate them, to relate them. And make sure to be able to relate everything you're doing in a Venn diagram, or rather a tree diagram. So this brings us to the end of probability. If you have any questions, feel free to WhatsApp me on this number for a quicker response.